Hello everyone. In this video we're going to talk about independent measures t-tests with effect sizes and confidence intervals. We'll first talk about what an independent measures design is and how do you know when to use the independent measures t-test, and then we'll talk about the 4 pillars of scientific reasoning. You have an independent measures design when you have separate groups of people in your study. So for an independent measures t-test, that would mean that you have 2 separate groups of people. So this could be 2 pre-existing groups. It could be people who currently exercise versus those who don't currently exercise. Or it can be 2 groups that researchers randomly assign people to. It could be like a drug group or a placebo group. Here we have an example of an independent measures design with pre-existing groups. So we're using this example where we have a population of people who exercise and another population of people who do not exercise. And so for our study, what we could do is take a random sample or a sample of people who exercise from that population, and then a different sample of people from the population of people who do not exercise. And then what we could do is measure a dependent variable. And so in this case, we could look at, say, the average systolic blood pressure for this sample of people who exercise and compare it to the blood pressure of people who do not exercise. So what we're going to do is compute a statistic to compare these 2 sample means to make an inference to what's the differences in the population between these 2 groups in terms of their systolic blood pressure. This next design here is an independent measures design with groups that the researcher creates. So here we have a population of people with high blood pressure, and then we take a sample of people with high blood pressure from that population, and then randomly divide them into 2 groups. One sample of people is given the drug, another sample of people is given the placebo, and which group they're in is determined by random assignment. Now then, for both groups, you could record the average systolic blood pressure of the people who take the drug, and then also the blood pressure of people who took the placebo. And we have sample means for those 2 groups, and we'll be comparing those sample means to make an inference about the true difference in the population between the drug group and the placebo group. This research scenario here is looking at a design where we have groups that the researcher has created. And the research question we're trying to answer here is, does walking outdoors increase happiness more than walking indoors? So research has shown that exercise can help increase people's psychological well-being, and research has also shown that being outdoors can increase psychological well-being. So based on this research, a health psychologist designs a study to determine if walking outdoors is more beneficial than walking indoors. And to test this hypothesis, she recruits a sample of 100 people from Chicago, Illinois to participate in the study. The participants are randomly assigned to either walk around a quarter-mile indoor track or to walk around a quarter-mile track outdoors. All participants walked 3 days a week for 45 minutes each time, and after 1 month of walking, the participants completed a survey that measured their subjective happiness on an interval scale. And we're going to use the 4 pillars of scientific reasoning to determine if walking outdoors increases happiness more than walking indoors. Here's a graphical depiction of this study design. We start with a large group on the left here, a population of people in Chicago, Illinois, and then we take a sample of people in Chicago to be in the study, and then further subdivide that sample into 2 groups. We randomly assign people to either walk outdoors or walk indoors. And then after they participate in these treatments, we have each group or each person in the group complete a survey where they measure their overall level of happiness. So we're going to use our sample data comparing the indoor and outdoor walking groups on their happiness score to make an inference to the actual difference in the population between these 2 groups. The dependent measure in this study is happiness, and we've operationally defined it as participant score on this subjective happiness scale. So the 4 questions here are listed on the slide, and researchers would compute an average score for these 4 scales. It's important to note that the score for question number 4 needs to be flip-flopped or reverse scored because it's in a different direction than the other items. But when you do this, when you take the average of these items, people typically treat this as an interval ratio scale, and so we're going to do the same, right? And the citation is there for more information about this scale if you're interested. Now we're going to use all 4 pillars of reasoning to investigate this question of whether or not walking outdoors improves happiness scores more than walking indoors. Our first pillar we're going to work with is hypothesis testing with continuous p-values. There are 5 different steps when you're doing hypothesis testing with continuous p-values. We're going to work through each of these steps on the following slides here. Our first step is to make sure we've chosen the correct statistic to analyze our data. In this case, we have 2 separate means from 2 separate groups of people. And we also have a dependent measure measured on an interval ratio scale. So an independent measures t is appropriate when you have 2 sample means that came from 2 different groups. And remember that you can only compute means if you have interval ratio data, not nominal or ordinal. Our next step is to determine if the statistical assumptions are met for this test. So all statistical tests have assumptions, and if these assumptions are violated, the results of the test might be misleading. So we're going to start by investigating these 4 assumptions for the independent t. Our first assumption is independence, and this means that each participant's score within a condition is independent of all other participant scores in that same condition. So this isn't an issue of statistics, this is a research methodology question. Was a study well done so that we know that individuals within a condition are independent of others? And in this case, we're going to assume they are. It was a well done study. Next, we have appropriate measurement, and that means that the dependent variable, in this case happiness, has to be measured on an interval scale, or a ratio scale, but we've already established it was on an interval scale. And then we also need to know whether or not we have a normal distribution of sample means. So remember that this is about the distribution of sample means, not scores. So you don't look at the scores in your data set to make this determination. This is determined based on sample size. So as long as your sample size is close to 30 or higher, then you're probably going to have met this assumption. Note that with sample size of 30 or higher, that means within a group. So in this study, we have a total of 100 people, and we have 50 per group. It's important that the per group number be close to 30. So because of this, we can be confident that this assumption is met. Our next assumption is homogeneity of variance. And what that means is that this test, the independent t, assumes that the 2 sample variances are estimating the same population variance. And the way we check this is by comparing the standard deviations in our 2 conditions. So we have 2 standard deviations here highlighted in red, the indoor and outdoor group. The indoor group standard deviation is 1.67, the outdoor group standard deviation is 1.79. So if you can look at those 2 standard deviations, you can see that they're pretty similar. And as a general rule of thumb, if one standard deviation isn't triple the size of the other standard deviation, the assumption is probably met. But there is a statistic you can use to actually compare these 2 means statistically, and it's called the Levene's test. The Levene's test compares the 2 standard deviations for your 2 groups and gives you a p-value. And that p-value is interpreted just like any other p-value. And that is, it's telling you the likelihood that the observed difference that you're seeing between these 2 standard deviations is likely to be due to sampling error. So the probability that I would get a difference between the standard deviations as extreme or more extreme than the one I observed is 0.115 here. So if your p is less than about 0.05, you can be concerned that the assumption is violated. If your p is greater than about 0.05, the assumption is probably met. But don't just look at the p-value. Look at the standard deviations to see how large the actual difference is, because sometimes you can end up with a p-value that's really low, even if you have a small difference between your standard deviations, if your sample size is really large. So be careful not to just use this as a rule, but as a rule of thumb, and look carefully at your data before proceeding to make sure that this assumption is met. In this case, our standard deviations are very similar. It's a difference of 1.79 and 1.67, and our p-value is greater than 0.05. So I'm confident that this assumption is met as I move forward. So even if your data violates this assumption, all isn't lost. There are actually two different t-tests. The student t-test is the one you use when the assumption is not violated, and that means the standard deviations are similar to each other. If the assumption is violated, in other words, the standard deviations are not similar, you can use the Welch's t-test. Statistics programs give you both t-tests, and then you just have to decide which one to report there. So for this example, we're going to use the student t-test because our homogeneity variance assumption wasn't violated. Our p was greater than 0.05, and also our standard deviations were very similar to each other. Our next step is to identify the statistical null hypothesis. So our null hypothesis states what the population parameters would be if there were no effect at all in the population. In this example, we're comparing the indoor and outdoor walking groups. And so if the null hypothesis is true, we would expect there to be no difference in happiness scores between these two groups. So you can state that verbally, but you could also state it using symbolic notation, where the population mean for the indoor group minus the population mean for the outdoor group is equal to 0. Or another way of saying that is that the mean to the indoor group and the mean for the outdoor group are equal to each other. Now we're doing a two-tailed test here because we are interested in results in either direction. It would be interesting to find that happiness levels were higher in the indoor group or if they were higher in the outdoor group. Our next step is to graph the sample data. So your software is probably going to have a slightly different looking graph than the one I have, but this is always a good practice to start with to get a sense of what your data looks like. So here I have graphs here comparing the indoor and outdoor conditions on their happiness scores. And I can see that it looks like the outdoor group has somewhat higher scores than the indoor group. Okay? So you can also note that in the outdoor group, our mean and median are very similar. In our indoor group, the median and median are not similar, suggesting a skewed distribution. But that's okay. Remember, the assumption of normality is not about my data, it's about the distribution of sample means. And my sample size of 50 per group makes me very confident that that has been met. Your next step is to compute the t and the p-value. In this case, we're computing the student t because we're confident that the assumption of homogeneity of variance was met. So we've provided the computations here for computing the t. You start by computing the pooled variance, which is each standard deviation squared multiplied by its degrees of freedom, and then you divide that by the total degrees of freedom in the study, which gives you a pooled estimate of the variance in the study, where if you had unequal sample sizes, it would give more weight to the sample with a larger size. In this case, our sample sizes are equivalent, so there's no weighting going on there. Next, we have the standard error of the mean difference, which is the pooled variance divided by n, divided by the pooled variance divided by the second n, and you take the square root of all of that, which gives you the 0.346. Now you'll notice that the 0.346 is in the output that we have listed here. It is the standard error of the mean difference listed on the output, but the pooled variance is not in the statistical output anywhere. If you need the pooled variance, you have to compute that by hand typically. And then finally, your t is the difference between the means divided by the standard error. So it's the observed difference divided by the difference you'd expect due to sampling error. So our t here is 1.27. In the output, you can see that that gives you a p-value of 0.206. And that p has 98 degrees of freedom, which is just the total sample size minus 2, or one sample minus 1 plus the second sample minus 1. Now we need to interpret our p-value. So this distribution here is a graph of all possible sample means of a given size with degrees of freedom equal to 98 taken from this population. And the p-value that we have comes from this graph where we look at the possibility or the probability of getting a t greater than the one that we obtained of 1.27, or since it's a two-tailed test, or less than negative 1.27. And that area there, or the probability of finding a score in one of those areas, is 0.206. So the probability of obtaining a t more extreme than 1.27 or negative 1.27 is 0.206, if in fact the null hypothesis is true and there's no differences between the indoor and outdoor walking groups in happiness levels, and also assuming there are no methodological flaws in this study. So with a p of 0.21, we can say that we're pretty confident these data are consistent with the null hypothesis, where there's really no difference between the indoor and outdoor groups on happiness scores. We had a difference of 0.44 between the groups, right? And that difference was very likely to be due to sampling error. The p-value tells us the probability that our results or our difference that we observed is due to sampling error. Now our next step is to look at the second pillar and look at practical importance with effect sizes. Effect sizes tell us if the results are large enough to have practical importance. And there are two different ways that you can look at effect sizes for the independent t. One is you can look at the raw scores. You can just look at the mean difference in raw score units. In this study, our mean difference was 0.44, and that was a 7-point scale, which is really not much of a difference. Now, in addition to looking at raw scores, you can also compute an effect size as a standardized d. And the d we're using is computed as the observed difference between the means divided by the pooled standard deviation. And if you do those computations, you'll find that our d is 0.25. We also could get it from statistical output from many programs as well. So what this allows you to do is compare effect sizes across studies with different measures of happiness. Right? So we used this one scale that had it was a 7-point scale, but other measures of happiness may have different scales that they're measured on. And so if you're going to compare across studies, you need to put them in a common metric, and D is a good common metric. We also have general guidelines for interpreting Ds, where about 0.2 is small, 0.5 is medium, and 0.8 is large. So a D of 0.25 would be a small effect, which is consistent with what we saw when we saw the raw score difference of 0.44 on a 7-point scale. Our next step is to look at confidence intervals to give us an estimate of how precise our population estimates are. In this study, we had 2 sample means, and we computed a mean difference between those samples. Now that mean difference gives us one estimate of the actual population difference between happiness scores in the indoor and outdoor groups. If we want to know how precise that estimate is in terms of its ability to estimate a population parameter, we can compute a confidence interval around that raw score mean difference. To do that, we're going to compute a point estimate, which is the difference between the 2 means, and add or subtract a margin of error to it. The margin of error is a t from a table. The t for the confidence interval comes from a table or an online calculator. And then you're going to multiply that by the standard error of the mean to get the confidence interval. Now you don't need to usually compute the confidence intervals by hand. Your statistics program will also give you the confidence intervals around that raw score and mean difference. So in this case, our lower bound is negative 0.25 with an upper bound of 1.13. So I can be 95% sure that the true population mean difference is somewhere between negative 0.25 and 1.13. Your statistics program might also provide confidence intervals around the effect size, which are also really helpful in interpreting the precision of the estimate. You can't do these by hand, so if your computer program that you're using doesn't provide them, you could use a different online calculator to obtain this. Right. So in this case, our effect size was 0.25. Our lower bound was negative 0.14 with an upper bound of 0.65. So we can be 95% sure that the true effect size in the population is somewhere between negative 0.14 and 0.65. Or this is anywhere from kind of a small decrease in happiness from walking outside compared to walking indoors, to a medium-large increase in happiness when walking outside as compared to walking indoors. And when interpreting your confidence interval, it's important to note that all of the values between the lower and upper bounds are considered to be plausible values, but those that are closer to the middle or closer to the actual mean difference or the effect size that you obtained those are more plausible than any out near the lower or upper bounds. So we have a distribution drawn here where you can see that outcomes that are closer to that midpoint of your sample data, or the sample mean difference, or the effect size D, are more likely than things closer to the other upper or lower bounds. We're done computing statistics now. Our last pillar is to take this data and put it into a scientific context, considering the research methodology and the scientific literature. Let's start by evaluating the methodological rigor of this study. So I know you may not have taken a research methods class yet, but you can still consider some of the issues relevant to this study. So thinking about, did the study, was it well done? Did it have proper controls? Was the independent variable manipulated well? Okay. In this case, was the study done with proper controls? Well, this was actually a pretty good study in that people were randomly assigned to two groups, and they both walked at the same amount of time. They both walked around a quarter-mile boring track. The only difference is whether they walked inside at a gym or outside, presumably in nature, right? Now, the question, though, I have about this study is, well, how well did we really manipulate that independent variable? First of all, did people really walk in both cases? Were they more or less likely to walk? We need to know that for sure. But also we should consider this idea of people outdoors being in nature. Now, depending on where this track is, maybe people walking around a quarter-mile track in an urban environment like Chicago don't really feel like they're out in nature. So maybe that variable isn't manipulated terribly well. Right? So this is an area for future research, right? What counts as being outdoors? What counts as being in nature there? Next, we want to determine how the study fits in with the current scientific literature. Right, the scientific literature suggests right now that there's benefits to both walking on happiness and also being outdoors. And so our results did not find that there was any additional benefit to being outdoors walking, but it's possible that maybe we need to consider more about what it means to be outdoors in nature. So we're not really sure at this point what the current state of the evidence is beyond what we have found. Now we're going to pull together all four pillars into one well-supported scientific conclusion. All right, so what you're going to start with here is an APA-style summary of the results. Other disciplines may have slightly different reporting styles, but they're all very similar to this, where you start by saying what statistic you computed. You computed an independent t-test to compare the happiness scores in the indoor and outdoor groups. Okay? So I have the mean and the standard deviation for both groups reported there. And then all of the analyses from computing the t-test, the p-value, and then the confidence interval around the mean difference, then the effect size, and then the confidence interval around that effect size. So all of these results come directly from your output. So you just have to make sure that you get them in there accurately. Now your next step after giving the statistics is to interpret and provide some context here. Now in a paper, this would typically be in the discussion section. So here we know that previous research has shown that both exercise and being outdoors in nature can increase happiness. The data from this study did not reveal any additional benefit to walking outdoors as compared to walking indoors. However, there may be limitations with this study. It's possible that walking outdoors in an urban environment is not really perceived as nature, and further research is needed to determine what types of outdoor environments improve happiness. Now, in class examples, you won't always have knowledge of the previous research or scientific methodology. If that's the case, just say that you don't have enough information to evaluate it. But it's important to keep this in mind, that your statistics do not occur in a vacuum. They occur in a big, rich context of both the study you conducted and the existing knowledge base in the discipline, and those need to be mentioned. So finally, we've pulled this all together in one big conclusion, where we start with a summary of our results, just give all the numbers in the first sentence. After that, it's helpful to provide another sentence here summarizing this in plain, simple English. Like I can just say now that, well, happiness scores were slightly higher in the outdoor group than the indoor group, but that difference is likely to be due to sampling error. And then follow that up there with your research and scientific context there. So if you're interested in reading a little bit more about this area, here are the two references that we refer to in this. This is by no means an exhaustive list. It's just meant to get you thinking about current research in this area and how what you've done in this particular example relates to the current research. So the purpose of this video was to introduce the ideas associated with the independent t-test. Now, if you want more details and more information about how to run the analyses and programs, or more details about specific elements of any of these 4 pillars, you can check out our website. All right, I hope that helps.